All right, guys, we'll get started shortly. Starting in a few minutes. If you can't check this out tonight, I'll make sure to get it up on my YouTube channel. Yeah. Do. Gonna get started soon. People starting to tune in. We'll start shortly. Starting shortly. All right? People starting to tune in. We'll start shortly. Starting Be right back. We'll start in a minute. All right, what we're doing tonight is the packet I gave you guys on Friday. It's just like 30 short answer questions. We'll be doing that. So feel free to take that out. If you don't have it, you lost it or otherwise, not a big deal. You can just follow along right here. So we're going to get started in about a minute. Just letting people tune in. If you don't have a Twitch account, that's fine. I've been told the delay is much better. It comes out much more smoothly than YouTube Live. So we're trying it out. If you don't have a Twitch account, you cannot say anything in the chat, but you can always message me on Remind. So just keep that in mind. So we'll get started in like a few minutes or a few seconds. If you have any questions, feel free to use the chat or text me on Remind. We're doing the review packet that I passed out on Friday. So feel free to have that out. And we'll get started shortly. Hope everyone had a good weekend. Enjoyed the snow. Had a good day off today. Yeah. Looks like people are starting to tune in. Got about 15 people right now. Let's try to get that up. That'd be good. Again, we're using Twitch because I've been told it works better. It's not nearly as delayed as YouTube is. I tried it out last night. It seemed to work okay. So hopefully you won't experience that lag between my audio and what pops up on the screen. But do let me know if you notice if it gets better or worse. I think now's a good time to get going. So I'm just going to start with question 1. Like I said, message me on Remind if you need me to stop or if I'm going too fast or if you have a question. Yeah, let's get going. So, first question on this review packet was about the chloride ion, Cl minus. And drawing ions has always been a tricky thing. So, first thing, whenever you're drawing a Lewis dot diagram, always double check how many valence electrons that atom has. And for chlorine as an atom, the valence electrons for any atom is always going to be the electrons in the last energy level. And for every single one of them in group 17, that's going to be 7, which implies that they have very similar chemical properties, because if you're in the same group, you have similar chemical properties. So chlorine as an atom, oops, wrong sheet. Chlorine as an atom has 7 valence electrons. Chlorine as a negatively charged ion is going to gain an electron. And I tried to come up with an acronym to remember if it's gaining or losing electrons when you're a positive or negative ion. And it was kind of hard. The best I could come up with was plenge. Plenge. Positive lose electrons, negative gain electrons. Plenge. So if you're a negative ion, you're always going to gain an extra electron. So chlorine should have 8 dots now. And an even bigger thing you need to make sure you do is put the charge on it. Make sure you indicate that it's negatively charged, so we know you drew an ion and didn't accidentally misdraw chlorine's atom. So whenever you see an ion, just put the charge right on there. It'll give it to you a lot of times, even in the question. So just keep that in mind. All right, explain why the electron configuration of 2711 represents a sodium atom in the excited state. So what does excited state mean again? Excited state means an electron has moved up an energy level. So it might have existed in the first, second, or third energy level, and it just moved up to a higher energy level. Maybe it went from the first to the third, or the second to the fourth, or the third to the fifth. It doesn't matter how or where it moves. If it's moving up an energy level, it becomes excited. And if we look at sodium in the ground state, sodium's electron configuration in the ground state is 281. So how do we know that sodium here is excited? Because an electron in the second energy level has moved to the fourth energy level. So if you see that electron moving up energy levels, you are now an excited atom. Everything in the ground state is on the periodic table in your reference tables. So you can just check there for what they are in the ground state. And if you see any of those electrons moving up, not gaining an electron is when you plunge it. Negative ions have gained electrons. Moving electrons means you've become excited. So in this case, sodium is excited. 3, I'm just going to erase so I have some room. Explain in terms of electrons how a strontium salt emits colored light. So this part here doesn't really matter in explaining the question. It's just getting at that excited to ground state idea. So when electrons, because we have to use the word electrons, move from excited to, and I'm just abbreviating here for time, ground state. That is when you see colored light. So we did a lab on this way back in first quarter where you lit different salts in a flame. You saw them make colored light. We also have a lot of practice questions where you have like a bunch of spectral lines and you have to identify which lines are in the mixture. All those questions are getting at how, or I should say, how that works is all about the electrons moving from an excited to a ground state. This is pretty important. This pops up almost every single year on the Regents in the form of a multiple choice or short answer question. All right, 4 through 7 I mainly put on there just as a little bit of a review of those people and who discovered what and when. The questions themselves I don't think were particularly hard. All you had to use most of the time was the data table here. But it was good practice just to see the different types of people, because these really specific questions we tend to forget easily. So state one way in which the Bohr model agrees with the Thomson model. You could say a lot of different stuff here. Something as simple as both have electrons. They both mention electrons as part of their atomic model. Thomson did not say it directly, but he did say negatively charged particles. So those are electrons. So electrons are negatively charged. The protons are positively charged, etc. I would say that's one way they agree. Just simple as that. Using the conclusion from the Rutherford model, identify the charged subatomic particle located in the nucleus. So, the data table doesn't really help for this question. The question is basically asking what's in the nucleus and what's charged that's in the nucleus. So the nucleus of the atom has your protons and your neutrons. And then outside of the nucleus are your electrons. You notice now I put those charges on there. What's that charged particle in the nucleus? They like to ask about nuclear charge a lot. When you see nuclear charge, you think proton. When you see nuclear charge, you think proton. Say one conclusion about the internal structure of the atom that resulted from the gold foil experiment. This you could get directly from here. There's two conclusions from the gold foil. They like this question a lot. Atom is mostly empty, and it has a dense nucleus, a small dense nucleus. They like to ask this in the form of multiple choice questions year to year to year. I'd say luckily for whoever took this Regents from a few years ago, lucked out with this being a short answer question with a lot of the answers right in that table. What was the first model to include electrons? This one, when I've given it on tests in the past, is always a little tricky because the first one that actually mentions electrons is Bohr. It says it right here. However, like we discussed earlier, Thomson called them negatively charged particles. Those negatively charged particles are electrons. So the first one actually mentioned it was the Thomson model. And the big thing to associate with Thomson is cathode rays. You hear cathode rays, you read cathode rays, you think to yourself, Thomson, electrons. Thomson, electrons. You see gold foil, you think Rutherford, empty atom, positively charged nucleus. Didn't mean to do that there. All right. Tried to put a lot of stuff with atomic structure because not only is that a big important unit, but that's a really easy unit to get confused on. This question, I believe number 8 here, is right from one of your tests. Explain in terms of atomic structure why barium has a lower first ionization energy than magnesium. So if we look at where barium and magnesium are on the periodic table, they're in the same group. And when you have to explain any of those trends in the same group, whether that trend is why does the radius get bigger as you go down a group? Why does the electronegativity and the ionization energy get smaller as you go down a group? The explanation is always consistently the same. So when you're going down a group, not in terms of stating what the trend is. Remember, it's stated what happened in the question. In terms of explaining it, in terms of atomic structure, barium has more electron shells. Don't stop at electrons. There are a lot of atoms on the periodic table that have more electrons than magnesium. Most of the periodic table has more electrons than magnesium. So you can't stop there. You got to talk about their shells. And how do you know this? Look at their electron configurations. So, magnesium has 3 shells, 2 in the first, 8 in the second, 2 in the third. Because their electron configurations you can always get from the bottom left corner of their symbols. Barium, on the other hand, has 6. 2 in the first, 8 in the second, 18 in the third, etc., etc. So I just got that right from the periodic table. So regardless of the trend, radius, ionization energy, or electronegativity, the explanation going down a group is always the same. More electron shells. The questions about going across a period, going left to right, that's all about greater nuclear charge. So greater nuclear charge, which is the same as an increase in protons. Because as you go left to right, the electrons are staying in the same energy levels or the same shells. RB here, you can kind of see behind the background, has 5 shells. You go all the way across in the same group, iodine also has 5 shells. So you can't just be talking about the electron shells because they're remaining the same in a period. You have to be talking about something else. There has to be some other reason. And that reason is the nuclear charge. There's more protons in the nucleus. They are attracting the electrons closer to the nucleus because opposites attract. Your positive protons, your negative electrons. So the protons are attracting those electrons. Therefore, you see a smaller radius as you go left to right. You see a greater electronegativity and a greater ionization energy. Speaking of these trends, whenever you have a question involving what is the trend, what is the electronegativity of this element, what is the radius of this element, is it bigger or less than this other element, you don't have to memorize that. That is all on table S. So if you go to table S, you could always look up the name and the symbol of these elements, what their radius is, what their electronegativity and ionization energy is. That's all available to you. So never worry about memorizing the trends. Just worry about memorizing or remembering why the trends occur. All right. Explain in terms of electron configuration why the elements in group 2 have similar chemical properties. We've already been over this. If you look at their electron configuration, all have 2 valence electrons. Obviously, you can't say 2 for every group because every group has a different amount of valence electrons. So you can say all of them have the same valence electrons for a question like this. Describe the general trend in electronegativity in group 2 on the periodic table in terms of increasing atomic number. So, since question 8 already mentioned it, why don't we just compare barium and magnesium, and if it gets lower from Mg to Ba, then we know the trend is it's decreasing. And if it gets bigger, we know that the trend is it's increasing. So, if you look at the periodic table, table S, look at Mg. Mg's electronegativity is 1.3. Barium's electronegativity is 0.9. That to me means it's decreased, so electronegativity is decreasing. Now, obviously, when you're on the midterm and you're answering these questions, make sure you use complete sentences. Don't say it. Don't say they. Don't just say decreasing. I'm just doing that for the sake of time, just so we can get through this in a timely manner. But when you're doing it on Thursday, make sure you use complete sentences with no pronouns. Identify a strong intermolecular force, aka IMF, that exists between water molecules but does not exist between carbon dioxide. So we got H2O versus CO2. The only real IMF that you should know for the Regents in this midterm is hydrogen bonding. If we're talking about types, not strengths of IMFs, then you need to know hydrogen bonding. Because hydrogen bonding is fun. You only see it between an HF, an HO, or an HN bond within a molecule, or between these molecules. So hydrogen bonding occurs with HF, HO, and HN. Obviously, we have an HO situation happening here. So that strong IMF, really the only IMF that you should be concerned with when it comes to regions chemistry, is hydrogen bonding. All right, next question. Draw a Lewis dot diagram for a molecule of hydrogen fluoride. When it comes to this test, usually Lewis dot diagrams, there's kind of a trick when it comes to like these simple ones that you typically see on the reagents. Usually I just draw their individual dot structures. So hydrogen has 1 valence electron, and you can get that from the periodic table. Fluorine has 7. And the general rule of thumb is, if an atom has a lonely electron, pair them up with a bond. These both have lonely electrons right there, so you can pair them up with a bond. Double check that you draw the dots back on fluorine, because every atom wants 8 electrons around it. Hydrogen is happy with 2, so do never ever put extra dots on hydrogen. You can also draw it like this, showing those 2 dots coming in the middle and being shared, because this is a covalent bond. They are both non-metals, and when they're both non-metals, they share their electrons. 13, identify the noble gas whose atoms have the same electron configuration as a potassium ion. Excuse me. Still a little sick. Getting better. We were just there. So first, we have to check potassium's charge, because when an atom becomes charged, it becomes an ion. So, what is potassium's charge? +1. So when potassium, first of all, potassium's K. Let's keep that in mind. When potassium becomes charged, it's +1. And if we plunge this, positive lose electrons, negative gain electrons. Plunge. Made that up earlier today. Hopefully it'll stick. That means potassium is going to lose 1 electron. So now it's 288. So let's go to the noble gases, which is group 18. And let's see who's 288. And would you look at that? It's beautiful argon. So, answer this question. Argon. Identify the 2 types of chemical bonding and the source of dietary potassium in this cereal. So, there's our formula. I see K. K is a metal. I see P and O. Those are both nonmetals. And when you have a metal with multiple different nonmetals, that metal bonds with the PO4 ionically, and then the P and the O are bonding covalently. So, metals and nonmetals means you have an ionic bond. Nonmetals only means you have a covalent bond. If you got both, put both. Compare the radius of a potassium ion to the radius of a potassium atom. So we just looked at the ion of potassium. We said it was K plus 1, which means it went from 2881 to 288, which means it got smaller. So the ion is smaller than the atom because it lost an electron. And when you're losing an electron, especially when that electron is lost in the final energy level, you get a lot smaller. So positive ions are always going to be smaller because they're losing electrons, and negative ions are always going to get bigger because they're gaining electrons. All right, identify the nucleus above that is found in an atom that has a stable valence electron configuration. So the first thing I would do when I saw this question, this was on the Regents, I believe, 2 years ago, is I would try to get all the protons and neutrons counted up for each nucleus just so we're ready to go. So Nucleus 1. I see 1, 2, 3, 4, 5, 6, 7, 8, 9 protons. And 1, 2, 3, 4, 5, 6, 7, 8, 9 neutrons. So 9 protons. Let's identify them. We'll get a lot of practice with this. 9 protons. If we look at the atomic numbers, zoom in, there we go. It's going to be fluorine because fluorine's atomic number is 9. And fluorine is the only element that has 9 protons. So this one's going to be fluorine. Let's get practice with the mass as well. What is its mass number? So mass number is protons plus neutrons. So the mass number of this nucleus is going to be 18. And if you were to write that out using its symbol, if we write it out in isotope notation, you always put the protons on the bottom left and the mass on the top left. All right, let's do that for all these, just for extra practice, just to make sure we're good with this stuff, because this does come up fairly often. Protons, we got 1, 2, 3, 4, 5, 6, 7, 8. 8 protons. If you go to the periodic table and look up the atomic number for 8 protons, you will get oxygen. So we got oxygen, 8. Neutrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 neutrons. 10 plus 8 is again 18. So the mass of this atom is also 18 because it has 10 neutrons and 8 protons. Nucleus 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 protons. If you go to the periodic table, you will discover that 10 protons makes you neon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 neutrons. So we got 10 protons. 10 plus 10 gives you a mass of 20. Nucleus 4. 1, 2, 3, 4, 5, 6, 7, 8 protons. We are oxygen again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 neutrons this time. So we got 8 protons. That's its atomic number. 11 plus 8 is 19. Something tells me they're going to ask a question about the 2 oxygen atoms. But we have identified all the atoms based on their protons. We have identified the mass of all of them by adding protons and neutrons together. Identify the nucleus above that is found in an atom that has a stable valence electron configuration. We are looking for a noble gas because they are the stable ones, which is group 18. Because every atom in group 18 has 8 valence electrons, which means they are stable. And the noble gas above is going to be neon, which, to answer the question, nucleus 3. So don't just say neon for a question like this. If it says identify the nucleus, make sure you say nucleus 3, because that's what it was asking for. Why do nucleus 2 and 4 represent nuclei of 2 different isotopes of the same element? This is a 2-part answer. They have the same protons, but different neutrons, and both are key. You have to say both. If you just say different neutrons, we do not know if you are an isotope. Many, many atoms have different neutrons. All of them probably have different neutrons than any other atom you could compare it to. So to make sure that you understand and that we know that you get it, you have to identify that the elements are the same with the same protons and that the neutrons are different, making them isotopes. Determine the mass number of the nuclide represented in nucleus 2. So a lot of people on this region actually got this wrong because they identified oxygen and then they went to the periodic table and they looked at the mass of oxygen on the periodic table. That's the atomic mass. That is the average atomic mass. That is not the mass number. The mass number is the protons plus the neutrons, which we did already because we counted these. and we counted 10 protons or 10 neutrons and 8 protons. So when you add those together, you get 18. So the answer to this was 18, not 15.99999. Identify the element that has the atomic nuclei represented by nucleus 1. This was F. We did that already. Identify the bonding in solid potassium. You would not believe how many students get this wrong because they say ionic. Ionic is a metal and a nonmetal. You need both. Potassium is just a metal. And since it is just a metal, all you need to say is metallic. Because if you're a metal, you just have metallic bonding. State the physical property that makes it possible to separate a solution by distillation. By definition, distillation means separation by boiling points. So the physical property is boiling point. We did this a while ago, so might need to jog your memory with mixture separation. Liquids can be separated easily by boiling point, and that process is called distillation. Explain in terms of charge distribution why this molecule is polar. Who cares about that? Who cares about that? As soon as you see molecule is polar, you will snap. Symmetry, nonpolar. Asymmetry, polar. So in terms of charge distribution, the charge distribution, make sure you actually say it, say the terms, is asymmetrical. Boom, done. 23. Explain in terms of electronegativity differences why a CO bond is more polar than a CH bond. So you need to go to table S. And when you go to table S, you need to look up the electronegativities of C, O, and H. And the further apart they are, the more polar it is. So the CO bond has a larger electronegativity difference. Not a larger electronegativity, a larger difference. Make sure you say both. Make sure you say both. In the space below, draw a Lewis dot diagram for the reactant containing nitrogen. N is nitrogen, not Na. Don't be a silly goose. Again, if we draw this simply, nitrogen, if you go to the periodic table, just so we double check, has 5 valence electrons. So, if you draw nitrogen, you go nitrogen 1, 2, 3, 4, 5. Hydrogen has 1 for each. So since each hydrogen has 1 electron looking for a buddy, and nitrogen has 3 electrons looking for a buddy, pair them up. H, H, H. Please keep in mind, H is happy with 2. So as soon as you bond it, you have an electron from H, you have an electron from N. That's a total of 2. You're done. Don't give H 8. State the direction excuse me, of heat flow between the air in the oven and the muffin batter when the muffin batter is first placed in the preheated oven at 200 degrees. This was on one of your quizzes way back when, and so many of you made just the silliest mistakes on this. It was kind of funny, a little sad, and made me feel weird. I don't know how to describe it. I don't know what was so hard about this question. But simply put, heat flows from hot objects to cool objects. The muffins were at room temperature. The oven is not. And generally speaking, if you weren't sure, if you're heating stuff up in the oven, then the heat is flowing to the thing that you put in the oven. So the heat is going from the oven to the muffins. Or at least the air in the oven to the muffins. A lot of students, I remember when I gave this question, were like, the heat's going to flow up and go into this and flow out of that. It's like, okay, let's take a break here. Let's remember these are Regents questions. They're worth a point. Give me a 1-point answer. Let's not make this complicated. All right, so when you read this, when you first see this, make sure you give that blurb a quick peek, because it's really easy to assume when you start to look at a cooling curve that it starts as a gas. First sentence, liquid sample. So we have liquid, solid, freezing. So the flat lines are always where the phase change occurs. So be really careful here. So that physical change is freezing, or you could say liquid to solid. Both would be acceptable. State what happens to the average kinetic energy of the molecules in the sample during the first 3 minutes. First 3 minutes is right here. Sloped lines, whether they are up or down, are always going to be a change in kinetic energy. Since this is a cooling curve, the average kinetic energy is going down because the substance is cooling. 28. Determine the total amount of heat in joules to completely vaporize a 50-gram sample of water. So, there's a lot going on here. First, it mentions heat. When you see heat, you think to yourself, go to the equations that involve heat. So heat is Q. So we're doing Q equals something, because all of these equations say heat is Q. The second word I circled was vaporize. So when you see vaporize, you think to yourself, let's pick the equation that mentions vaporization, which is Q equals mHV. The next thing you need to look up is what is HV. That is on the front of the reference table where it says heat of vaporization, which is 2260 joules per gram. So let's put that all together. Q is what we're looking for because it's asking what is the total amount of heat. The mass was 50 grams times HV, which was 2260 joules per gram. Your grams will cancel out. You'll be left with just joules, which is what we were looking for. And you just simply multiply those two numbers together, and you'll get 11,030 or 11,300, right? I think so. 11,300 joules. I just did that in my head. I'm pretty sure that's right. But you have an answer key. You can double check. 29. Show the numerical setup for getting the volume of a gas in cylinder B at STP. So, UCP, UCV, UCT. Well, you're probably going to use the equation that has PV and T. And the only equation that has all that is P1V1 over T1 equals P2V2 over T2. Let's do this. Next thing it said was STP. You're like, oh my God, I don't remember what STP is. It's on the reference table. So there's STP. Make sure you always use Kelvin, not 0 degrees Celsius, or you're going to get an answer that doesn't make sense. And then make sure you choose the pressure that matches the units that have already been either 1, provided for you in the question, or 2, provided for you somewhere else in the question. I just say the same thing twice. Let's try that again. 1, provided for you in the data somewhere, or 2, asked directly by the question. So in this case, let's see what they did. They didn't ask for it in the question. They didn't say make sure you use atmospheres or something. But in the data, I see atmospheres, I will use atmospheres. So, setting it up, you got P1 from here, V1 again from here, divided by T1, equals P2, which will be 1 atmosphere from STP on the reference table, times V2, which we're solving for because it asks you to determine the volume, divided by T2, which is STP. You will cross multiply and divide here. And I'll finish this setup, but I don't have a calculator handy. So, again, you have a key. We got 1.2 times 1.25. I'm going to run out of room. Times 273, because we multiplied all these together here. You'll divide both sides by 293, and you'll get your V2, which will change a little bit because your pressure went down. So your pressure went from 1.2 to 1. So a pressure down usually means volume will go up. But your temperature also went down, which means volume will also go down. So it's going to change a bit, but not too much. 30. Show numerical setup. So do not solve. Just set it up. Heat, which means we're doing Q. Temperature, which means we're doing MCAT. From 0 degrees to its final temperature. So we're calculating the heat, so we don't know Q. It's a 200-gram sample. C is on the reference table right here. Specific heat capacity. That's what C stands for. Mr. G, how'd you know what C stands for? I don't remember what C stands for. Oh, it tells me. So when Q equals MCAT, what do all these variables mean? Well, just look. It means specific heat. So the specific heat for water is 4.18. Times delta T, which means change in temperature. So that is final minus initial. And that's it. If any of you have chemistry-related questions, I just wanted to go through all these. I know you had a key, but it's good to kind of think these through, see my thought process, go over additional parts of these things that might not appear in the question, like going over ions and charges and electrons. But if anyone has a question, all 2 of you, it seems, that are checking in, please ask now, either in the chat room or on Remind. I'll give you a minute. If not, I'm heading out. Question 1. Not a question, more of a demand. Harper!
Go see Dad.
Come here.
Oh, this is going to take some convincing. Come on. Here, give her a treat. Hi.
She's coming. Come here.
You gonna take your phone in to see your kids?
What's this? Come here. Get up. Jump up. Jump up. Come here. Yeah. Come here. Come closer. I don't know if they saw you. Get up. Up. Where are you going? Come here. Come on. Come on. Get it. Get it. Get it. You can do it. Oh, no. You're just going to give me paw? Harper. See, Harper, I have the bone. It's a Mrs. G night.
It's a Mrs. G night. Hey,
Come here.
Hi. Oh, she just figured out you have the bone.
Oh, yeah. There she is. Who's your good girl? Yep, see you later. Thank you. Thank you for the treat.
Come on.
Bye. Anything else? Chemistry related, as I'm choking. Chemistry questions going once. Twice. Sold to nobody. So, I'll put this on my YouTube channel if you couldn't check in. Everyone else that tuned in, thank you. Thank you for thinking about chemistry, even though you got a bunch of other midterms. I get it. And I will... Whoa! 2 reminds. What is happening? All right, what if you don't know the C in MCAT? Like, what if it's not water? It's pretty much always water. And if it's not, they're going to give it to you. They don't have the expectation that you have to memorize a bunch of random C values. So if you don't know C, it's provided somewhere. If it's water, it's on the reference table. If it's not water, they'll give it to you. Good question. You guys are great. And by guys, I mean that one student that's asking away. You're the best. Anything else going once? Going twice. Sold. I'm heading out. I don't know what they normally say on Twitch. Make sure you smash that subscribe button. Give this video a like. Who knows? If you're checking out my YouTube channel, if you're checking out this on YouTube, obviously subscribe. Turn on notifications. Like, comment. You know the deal. Good night.